Hi everyone, I'm Sharzad. I'm a PhD student working with Dr. Torrance and Dr. Kellerup on a bioremediation project. And today in this module, we're gonna talk a little bit about EPA history and the Superfund sites, the bioremediation processes, and sampling and monitoring Superfund site. So first, I'm gonna talk about EPA history very briefly. So the information you see in this slide and the next few slides can easily be found on EPA website. This is just a summary for you guys to see the whole picture more easily. But if you want to get more information, you can definitely check EPA website. So in 1962, the book Silent Spring was published by Rachel Carson, and in the book she basically talked about how pesticides can kill the birds and therefore silent the forests, hence the silent spring. She also talked about different chemicals that can cause danger to environment and animals and human. So it is considered the start of environmental movements, basically. In 1969, Cuyahoga River, I hope I pronounced it right, caught fire because it was so polluted, and it brought a lot of attention to water pollution in the country. In 1970, President Nixon signed a bill to form an EPA, and finally, on December 2nd, 1970, EPA was officially established. So EPA performs different compliance monitoring programs with its partners. You can see a list of these different compliance monitorings. Each of them focuses on a specific aspect of EPA mission to make sure that air, water, and the land is clean. So, like, obviously, Clean Air Act, for example, focuses on standards for air pollution. Clean Water Act focuses on different standards for wastewater discharge. Superfund or CERCLA compliance monitoring is actually what we're going to talk about more, so I'm going to talk about it in more detail in the next slide. You can see the rest of these compliance monitoring programs here as well, and again, definitely if you want to get more information about any of these, you can check the EPA website. So, CERCLA, or Comprehensive Environmental Response, Compensation and Liability Act, was passed in 1980. It basically gets contaminated sites cleaned up by first finding the companies and people responsible for the contamination, and then negotiating with them to either clean it up themselves or pay EPA or a third party to clean it up for them. So it establishes prohibitions and requirements for closed and abandoned hazardous waste sites, provides liability of persons responsible for release of hazardous waste at the sites, and establishes a trust fund to provide for cleanup when no responsible party could be identified. And it is able to do this because it creates a tax on chemical and petroleum industries, and over 5 years, it was able to collect $1.6 billion that went into a trust fund for cleaning up abandoned and uncontrolled hazardous waste sites. So this is an overview of this law, which authorizes two kinds of response actions. First, the short-term removals, which targets the threats or releases that need immediate responses, such as like oil spills, for example. And then we have the long-term remedial response actions, which permanently can reduce the concentration of hazardous substances and therefore the danger associated with them, and are usually conducted. These actions are usually conducted on EPA's National Priority List, or NPL. So NPL is basically a list of sites of national priority that are known for hazardous, having contamination or hazardous substances, and um, basically guides the EPA to find the sites that need more investigation. So how does this work? EPA have some different methods to find out about a contaminated site. They can receive a phone call from citizen. It can be a reported accident, or sometimes a planned search to discover contaminated sites. And after the report, they collect information. They talk to people. There are some sites that can meet certain requirements to be treated like by federal action, and after that, EPA tries to rank these sites that are qualified based on this ranking system that they have, hazard ranking system, or HRS. And this system, they basically try to find out how likely it is for a person or environment, like water, air, animals, to be exposed to the substance, to that contaminant, and how likely it is for them to be harmed by this exposure. So the sites with high HRS will be put on National Priority List, or NPL, which is, as I mentioned before, basically a list of nation's worst contaminated sites. And the way this works is, first EPA publishes the intention of putting this site in NPL, and publishes the intention in local media and for the community to review. Then after the official comment period, if the site still meets the certain requirements to be cleaned up by the Superfund, then the site will be officially put on the NPL list. And after that, basically EPA does their remedial investigation and feasibility study, which determines the contaminant, the extent of contamination, and the technologies that can be used to treat the contamination, the cost, and stuff like that. So at the cleanup process, EPA actually first proposes a plan with a list of cleanup options, and also mentions which one they prefer themselves. The public has like 30 days to review the plan and comment on it. Again, EPA responds to the comments and finally publishes a record of decision, which is basically a statement of exactly what they want to do with the site and how they want to clean it up. Then during the remedial design, remedial action phase, they mostly get prepared and finalize the cleanup process, and some of the cleaning up process will happen during this phase. And during the construction completion, the physical activities that are necessary for the cleanup method are completed. In this phase, not all the cleanup goals might have reached, but the physical, like if they need to construct something, it has been completed. During the post-construction completion, they usually operate the constructions and maintain them, and they monitor the cleaning up process and make sure that everything is going well and the cleaning up process is going well, and also make sure that no human exposure happens in the site. Then when all the cleanup goals are met and all the requirements are met, and the EPA publishes a letter that with the intention of deleting the site from the NPL. Again, the answers to the public concerns, and finally officially remove the site from the NPL list. And at the end, the EPA works with the communities through partnerships and activities to help the the sites to be reused. They can be used again for different purposes, like commercial, industrial purposes, for housing, for wildlife preserves. And here in these pictures, each of them actually show one site that was in the NPL list and was deleted from that, and now is being reused as wildlife. So now we have somehow reviewed what EPA does. Now we want to talk about different remediation methods. So the conventional remediation methods that we have are dredging, capping, incineration. In dredging, you just dig up the contaminated soil or sediments and move it to a landfill. In capping, you cap and contain the material in the area. And in both of these methods, you're not really getting rid of the contamination. You're just either containing it in that place, or moving it into a new place. And incineration obviously has its own environmental problems. Bioremediation is somehow a more environmental friendly option usually, and it can be categorized in two different sections. It can be either ex situ, where you physically remove the contaminated material and treat it and put it back, like pump and treat, where you remove the groundwater, you treat it outside, and then you put it back. Or in situ bioremediation methods, which you treat the contaminated material in place, and they're usually much less expensive than the ex situ options. So what is bioremediation? It is basically stimulating the activity of different organisms to clean up contaminated soil, sediments, and groundwater. As you can see in the figures, different microorganisms are able to use these contaminants as food and produce gas and water, and like degrade that contaminants. And bioremediation can be used for removal of oil, petroleum products, solvents, pesticides, or even inorganic materials such as uranium. So it can be used for a wide range of materials and contaminants. And like here you can see the oil droplets surrounded by these hydrocarbon oxidizing bacteria, which can degrade these oil droplets and use them as food. And here I just want to introduce this term bioaugmentation, which is a type of bioremediation, and it is when we introduce a specific microorganisms to a contaminated site. So now we want to zoom in a little bit. We want to focus on bioremediation of organic pollutants. So we can categorize organic pollutants into two different categories. They can be natural organic materials such as oil, which are produced naturally, and we also have xenobiotics that are not produced by organisms in nature. Usually human produce them in the labs. And the natural organic materials are usually can be eventually degraded into carbon dioxide, and many different microorganisms are able to process them because microorganisms are used to their structure, and they have the enzymes needed to break down these materials. But xenobiotics are usually more persistent and can be degraded only by very few specialized microorganisms that have the enzymes to break down these structures. And you can see on the right different structures of some of these organic pollutants like DDT or trichloroethene that we're going to talk about today actually. So focusing more on bioremediation of xenobiotic pollutants, which are compounds like polychlorinated biphenyls, PCBs, chlorinated solvents, dyes, or pesticides. These compounds are usually so different from all the natural compounds that microorganisms usually experience, that they're not familiar with their structure, and therefore it is much harder to degrade them. And sometimes some of these organic xenobiotic pollutants can only be degraded when there is another source of organic compound around. In these cases, that organic compound usually acts as the target material that the microorganisms try to use, but at the same time, the enzymes that they produce to degrade that organic compound happens to be able to degrade some of the xenobiotic compound as well. So this process is called cometabolism. Cometabolism is usually happens usually very slowly, and usually causes the partial degradation of the xenobiotic pollutant, and that is not always good, because sometimes these intermediate compounds that form are actually even more toxic than the original compound. So this is one of the things that we should keep in mind when designing these processes. Also, the structure of compounds, temperature, pH, redox conditions, and organic content of the soil are the factors that can actually affect the degradation of these compounds. And here you can see like the degradation process of an herbicide called 2,4,5-T. As you can see at the beginning, a molecule of acetate should be separated to make the molecule simpler. Then a very specialized aerobic bacteria is able to remove chlorine atoms from the molecule, and then using the enzyme deoxygenase, this aromatic ring breaks up, and it becomes a much simpler compound that other bacteria can also use as organic compound and probably degrade it. So as you can see, it's not a very straightforward and easy. For in situ bioremediation of organic pollutants, we usually need the right microbes in the right place with the right environmental factors. The factors that we just talked about, like pH, temperature, redox conditions, and things like that. And just like any other method, bioremediation also, like in situ bioremediation, also has advantages and disadvantages. Some of the advantages are that, first of all, it can be done on the site, and that causes it to have a very low cost usually comparing to other methods. And also it causes minimum disruption to the site. Also, this method usually eliminates the contaminant permanently, and because it is environmental friendly, it is more acceptable by the public. We can also combine these methods usually with other chemical or physical methods. So these are the advantages of using in situ bioremediation. But some of the disadvantages are that not all the chemicals are biodegradable, or in an efficient time, or not biodegradable in a reasonable amount of time. Also, in some cases, as we just talked about it, the metabolism of these compounds can produce toxic byproducts or intermediates, which might be even more toxic than the original compound. So we should keep that in mind. Also, for each site, we have to check all the factors to make sure that we are providing the right conditions for the right microorganisms to be able to biodegrade the compounds. So we have to check if we have the right microorganisms there. We have to make sure that we have the right numbers of them in there. So for each site, it should be tailored specifically for that site and condition. So here you can see a map of the United States. I just got it from this link here. You can check it out, the map of different, like the Superfund sites around the US. But when we see one of these Superfund sites, and we want to find out if we can do a bioremediation for this site. We have to first find the answers to these questions. Like, first of all, is this contaminant biodegradable at all? Can this biodegradation happen naturally in this site? Do we have the right environmental conditions for the biodegradation? And we also have to make sure that the intermediates that are produced are not toxic, or we have to find out where do they go at the end, where will they end up, in water, in air, and can they be degraded again or not. So now I just want to go through an example of one of these Superfund sites. This specific site is located in Beltsville, Maryland. It's the project that I'm working on as part of my PhD dissertation. So it is very close by. It's owned by USDA, and it was once a landfill to dispose of masonry construction debris, tree clippings, wood, and broken asphalt. We are going to go through some of the steps that the EPA and the USDA took to find out about the contamination and what was their remedial plan, and now how they're monitoring it and sampling it. So as I mentioned before, this site was a landfill which was capped in 1980s. In 1991, a preliminary assessment and site investigation was conducted. Due to limited information that they had about the substances that were disposed of in the field, they didn't have any indication of hazardous substances being present in this landfill. But the groundwater samples that were collected at the time from 4 existing monitoring wells didn't show any hazardous substances being released from this site. So they considered this landfill to have low risk. But in 1996, a field reconnaissance was conducted, and they didn't find anything on the landfill, but they found 3 empty 55-gallon drums and a large compressed gas cylinder in the woods around the landfill. And in 1991, a baseline groundwater sampling was conducted, which was basically to find out if these 4 existing monitoring wells are useful, and if possible to collect some groundwater samples to characterize the site, and also to collect some groundwater samples to look for possible potential contaminants. In 1998, they collected desktop data, which is basically interviews with the employees at the site. During these interviews, they found out that the monitoring of the disposal activities at the site were poorly conducted, and they found out that there is a possibility of finding hazardous substances at the site. So finally, in 1999, a site screening was conducted. So they collected samples not only from the wells, the existing monitoring wells, but also they collected groundwater samples from the perimeter of the landfill using geoprobes. So they drilled into the groundwater. They collected groundwater samples. Also, they collected surface water and sediment samples from close by areas close by to the landfill and tested them. So the site screening identified the compounds of potential concern, which were mostly chlorinated volatile organic compounds such as tetrachloroethene or PCE, and also the breakdown products of these compounds like trichloroethene or TCE. So the next step was the remedial investigations, which were performed in 2002 and 2003. In this during this investigation, they collected different types of samples like soil gas, soil, groundwater, surface water, and sediment. And they also conducted baseline human risk and ecological risk assessment. So, soil gas samples basically measure the gas contained in the interstitial spaces of the soil, and it was used to locate the contamination, basically identify the location of the contamination. So here you can see this line shows the landfill, and in the south of the landfill you see this contamination, and mostly in the southeast. And here is the surface water that we're talking about. So it basically is located mostly in the south of the landfill. So soil samples and groundwater samples were also used to characterize the contamination and the area of contamination. TCE and its degradation products were detected in all the environmental media sampled with the exception of stream sediment. And the TCE concentration was higher than the maximum contaminant level in Safe Drinking Water Act. And so the remedial investigations basically concluded that the primary contaminant in the site is TCE and its degradation products. So we used soil samples, groundwater samples, and soil gas samples to first find the pollutant and then the location of the So now I want to talk a little bit about TCE itself. So TCE, or trichloroethylene, is a chlorinated aliphatic organic compound. You can see this structure here on the right. It is highly oxidized, and it was used as a metal degreasing compound and industrial solvent and a dry cleaning reagent. And it can cause cancer, and it can affect the central nervous system. It can adversely affect the kidney, liver, reproductive organs, and immune system. So, as I mentioned before, TCE degradation products were also identified as contaminants of concerns in this site. So these are the TCE degradation products, vinyl chloride or VC, and these two are isomers of dichloroethylene or DCE. And you can see the structure of these compounds on the right. And vinyl chloride is actually the most toxic degradation product of TCE, and you can see it has the lowest maximum contaminant level among these chlorinated solvents that we have here on this site. The proposed plan for the remediation of this site was to install a mulch biowall and enforce land use controls, or LUCs. So let's look at the map actually. Here again, this was the landfill, and this is the groundwater flow direction. And if you remember, this was the hotspot for TCE contamination. So the idea was to build the biowall, this one here, against the flow direction and in between the plume and the surface water. So they published this proposed plan, and after reviewing the public comments, they published the record of decision in 2011, and in 2013, the biowall was actually installed in the site with 40% sand, 30% compost, and 30% mulch. We're going to talk about what is a biowall. Biowalls are these permeable trenches that are placed in the subsurface, usually down gradient the plume, to capture it under its natural gradient. So it creates this passive treatment system. As you can see in this figure, the contaminated water passes through the biowall. Biowalls are usually amended with, so they usually contain organic materials to promote the growth of bacteria, and these bacteria are able to degrade the contaminant. and then the clean water, after all these reactions that happen inside the biowall, it can be adsorption, it can be biodegradation, and other reactions. The clean water can will come out of the other side of the biowall. In the case of this biowall that was installed in BDRLF site, just to give you an idea of the size, it was 25 to 35 feet deep, 1 to 3 feet wide, and 1,000 feet long. So the mulch is actually used as a natural organic substrate to promote the growth of bacteria, and sand and gravel was used to maintain the permeability and prevent the compaction of the biowall. Different materials can be used for the biowall. Like here we used mulch, but other organic compounds can also be used as the filling material for the biowall, like vegetable oil or compost or other organic materials, depending on what compound you're trying to get rid of. So there are some benefits in using a biowall, like it is able to degrade the plumes continuously without the need to bring them to the surface, which makes them cost effective, and they can operate for years with minimum to no maintenance. And because there's no above the ground installation, the property can be used for other purposes while being remediated. And this method is one of the most frequently used methods for remediating chlorinated solvents contaminated sites. So TCE under anaerobic conditions can go through degradation by some bacteria, and the process is called reductive dechlorination. In this process, the bacteria are able to reductively replace one chlorine atom at a time with hydrogen atom. So every time they take one chlorine atom and they replace it with a hydrogen, so they form DCE first, then vinyl chloride or VC, and then we have ethene with no chlorine atom left, and this is the benign product that we are looking for in TCE dechlorination. Genus of Dehylococoides, like the members of this genus are among the very few bacteria who are able to dechlorinate TCE all the way to ethene. So this genus in general is very important for bioremediation of chlorinated compounds. And Dehylococoides mccartyi, which is one of the species, one of the members of Dehylococoides genus, is actually, you can see it in the figure here. So before installing a biowall, we have to do a lot of aquifer testing to characterize the groundwater, and one of the most important factors that we need to find out is the groundwater velocity. So how do you think the groundwater velocity can affect the bioremediation process? It can actually directly affect the contact time between the contaminant and the biowall material, right? So say you want to, so you designed the biowall to promote the growth of bacteria and degrade the contaminant. If the lower groundwater velocity you have, you're gonna have a higher amount of time, much more time for the bacteria to contact with the contaminant and degrade it, and so it becomes potentially more efficient. If you have a lower groundwater velocity, you're going to have higher contact time or higher residence time inside the biowall. So it is very important to know that. And TCE itself, TCE velocity, is actually lower than the groundwater velocity. Again, do you have any idea why? And the reason behind this is actually because TCE is an organic compound, and because of that, it can easily absorb to the organic substrates in the biowall. So based on the organic carbon fraction of the biowall, we can actually calculate a retardation factor for TCE, and that is why the TCE velocity itself is lower than the groundwater velocity, but we have to calculate all of that ahead of time. And here in this table you can see the aquifer testings that were done for the BDRLF site with different methods to calculate the hydraulic conductivity and also the groundwater velocity, and later to calculate the residence time. The interesting thing to know is that actually these testings, this table you're seeing here, it was conducted in 2016, 3 years after the installation of Biowall. So what happened was that before installing the Biowall in 2013, they did a bunch of aquifer testings, but apparently they miscalculated the groundwater velocity. So the Biowall that they installed and designed is not efficient right now in degrading the TCE. So the TCE is being degraded, but a lot of intermediate products are being seen, while not much final benign product is seen. So that actually shows that the remediation process is not effective, and it can be the reason behind it can be the fact that the residence time was calculated wrong. And so yeah, in 2016 they did another sets of aquifer tests to find out the real real residence time for the groundwater, and they found actually it is much lower than what they expected. So they have to come up with other ideas right now to make the Biowall more efficient and to remediate the TCE completely. So after the construction of the remediation method, like in this case the Biowall, is completed, then we have to start the monitoring processes, right? So we have to monitor the conditions on the site to make sure that the remediation is happening the way we want it to. So these are a bunch of questions that you can ask yourself, or make sure you answer while you're designing a monitoring program. So like, what are the important parameters that you need to monitor for this specific site, or what kind of tests you're going to do and why, and which locations you're going to do that, and at the end, how do we know that the remediation is completed? So monitoring at BDRLF site is mostly focused on groundwater sampling, because TCE, although it is an organic compound, but it is relatively more soluble in the water than many of the bigger organic molecules. So it is mostly in aqueous phase, and so the first thing we want to monitor is the concentration of chemicals of concern. So we collect groundwater samples and send them to the lab to be analyzed later for concentration of TC and its degradation products. And as I mentioned before, TC degradation products are all toxic. So not only they're harmful, but if we see the accumulation of these compounds in the groundwater, it means that there's something wrong and the remediation process is not efficient. We also obviously look for the concentration of final benign products, in this case ethene and ethane. Geochemical and physical parameters are also very important, because they can not only control the behavior of our organic pollutant, but they can also affect the behavior of inorganic minerals and microbial population. So by checking all these parameters, we make sure that we know what is going on exactly in the groundwater, and we can also monitor the predominant microbial metabolism mode by looking for these electron acceptors like ferric iron, nitrate, and sulfate. Also, reductive dechlorination happens in a very reducing condition. So by monitoring these parameters, we can also find out about the redox conditions and see if we are where we should be. Physical parameters can also affect the microbial community and very much, and the microbial community, they're very usually sensitive to temperature and dissolved oxygen. As I mentioned, reductive chlorination happens anaerobically, so we should have 0 to very low concentrations of oxygen. Dihalococoides also acts and works in a very specific pH range, like 6.8 to 8. So we want to constantly monitor these parameters to make sure everything is right. And if something is off, then we can go back and amend the Biowall with something to make the conditions right again. So in this table here, I've kind of summarized the monitoring plan for the BDRLF site. You can see there are different types of wells. For example, these are the Biowall wells. They're all located alongside of along the Biowall, and they are the ones that are being monitored most frequently. Then we have the transect wells. They're located at the BW6, close to BW6 Biowall well, and they're perpendicular to the Biowall, so that we can find out more about the conditions immediately up gradient and immediately down gradient from the Biowall. Then we have the remediation investigation wells, or the MW wells. They're spread out on the field. I just highlighted some of them. And then we have the surface water monitoring plan, which happens semi-annually. So in this table, you can find out like different parameters that are being monitored and how frequently the monitoring is happening. And this table just shows the different methods that are being used for sampling and analysis of these parameters. So EPA has different methods, and which are basically guidelines and protocols for analysis of each of these parameters that will help us to collect representative samples and also to analyze them most efficiently to get the best results. Why is the sampling plan important? In order to make scientifically based decisions, we need accurate data and the data that is enough to draw conclusions. And to generate this data, we need to consider the appropriateness and accuracy of the sampling collection and sample collection and handling method. We also have to consider the representativeness of the data with respect to the objective of the study. And these two are being addressed in the sampling plan. That is why we have to put a lot of thought into designing a sampling plan ahead of time based on the objective of the study.